Identifying boundaries and forming different topologies typically assumes some compatibility with the metric of the manifold. In topology, the focus is primarily on the properties of the space that are preserved under continuous deformations, such as connectedness and compactness, without necessarily considering the specific metric. However, when considering specific immersions or realizings of these surfaces in a geometric context where a metric is involved, the feasibility of certain identifications depends on the metric properties. Here's a breakdown of how the metric comes into play. In pure topology, identification of boundaries to form new surfaces like a torus, a Klein bottle, or a Mobius strip is considered without reference to a specific metric. The resulting topological space is studied up to homeomorphism, which does not depend on the metric. To realize these topological surfaces as embeddings in Euclidean space, the metric must allow for the specific identification. If the metric does not allow certain identifications smoothly, the resulting surface might have singularities or other complexities. For instance, identifying boundaries of different lengths in the Euclidean space directly without stretching or compressing could create a manifold with discontinuities. While topological identification focuses on the qualitative aspects of the manifold, realizing these identifications in a specific metric space requires compatibility with the metric properties. This compatibility determines whether the identification can be made smoothly and whether the resulting manifold can be embedded or represented in a given geometric context. Incompatible metrics can still be studied within the realm of geometry and topology, even if it introduces quirks like singularities. Manifolds with singularities, they can still be of great interest. The singularities often provide insight into the structure and properties of the space. Even with an incompatible metric, topological invariants are properties that remain unchanged under homeomorphism. They can be used to study the manifold. The Euler characteristic is a topological invariant that gives a broad stroke of classification of manifolds. Homology and cohomology provide information about the structure in different dimensions of the manifold. It is appropriate and often useful to specify local topology in terms of local homeomorphisms, particularly along the boundary. This approach can provide a detailed and precise description of how the local structure of the manifold behaves near the boundary and how it changes under various identifications. Here's how this can be done and why it is beneficial. A homeomorphism is a continuous function with a continuous inverse. When focusing on local homeomorphisms, we examine the local behavior of the manifold around each point, ensuring that small neighborhoods around each point are homeomorphic to small neighborhoods in another space. Specifying how the boundaries are identified or mapped using local homeomorphisms helps in understanding the topological changes that occur due to these identifications. By using local charts, we can describe how each part of the boundary is identified. Transition functions describe how local charts overlap and transition into each other, providing a way to understand the global structure from the local data. An atlas is a collection of local charts that cover a surface. Each chart is a homeomorphism from a region on the surface to an open subset of Euclidean space. Along the boundary, these charts explain how the manifold looks locally and how it is glued to other parts of the manifold. Classifying singularities when dealing with them on a manifold the local homeomorphisms help in the understanding and classification. For instance, the local topology around an apex can be described using the local homeomorphism to a Euclidean disk with identified boundary. Local homeomorphisms allow for precise descriptions of how local neighborhoods behave and are connected, which is critical for understanding complex topological structures. This method accommodates a variety of boundary identifications, including those leading to non-standard or singular topologies, providing a unified way to describe different topological configurations. By piecing together local homeomorphisms, one can build a comprehensive understanding of the global topological structure, even if the manifold has singularities or complex boundary identifications. For each region around the boundary, you could define a local chart that maps this region homeomorphically to an open subset of Euclidean space. Use transition functions to specify how these local charts overlap and how the boundary points are identified. This includes specifying any twists or orientation in the identification. Study the global structure resulting from these local specifications, examining properties like connectedness, compactness, orientability, and the presence of singularities. Specifying the local topology in terms of a local homeomorphism along the boundary is a powerful and precise method for understanding how a manifold's local properties influence its global topology. This approach is particularly useful in differential topology and geometric topology, providing clarity and detail in the study of complex topological surfaces and their boundary behaviors. Typically, for the identification to maintain a well-defined topology, there should be a one-to-one correspondence being identified. This ensures that the identification is consistent and the resulting manifold is well-defined. However, it is possible to have more complex identifications where multiple edges or boundaries combine to identify with a single boundary. But this can lead to manifolds with singularities or more complex topologies. In a one-to-one correspondence, each point on the boundary corresponds uniquely to a point. And this is the most straightforward way to create well-defined topological manifolds. However, there are more complex identifications where we are combining multiple boundaries in such a way that in some cases you might want to identify multiple boundaries with a single boundary region. But this usually leads to singularities or more complex topological structure. In complex topologies that are more sophisticated, such as certain types of branched surfaces, multiple edges can combine to identify with a single edge, leading to branch points where the surface locally looks like multiple sheets coming together. And non-one-to-one identifications can create singularities where the surface is not smooth or the local structure is more complex. If multiple edges are identified with a single edge, the resulting surface may have points where the local topology is not homeomorphic to Euclidean space anymore. These manifolds might still be studied using topological invariants like the Euler characteristic, but the presence of singularities adds complexity to the analysis. While a one-to-one correspondence between identification is the standard approach for creating a well-defined topological manifold, more complex identifications are possible and can lead to interesting and complex topologies. These complex identifications often result in singularities or branch points, adding to the richness of the manifold's topology, but also complicating its analysis. Whether or not such identifications are desirable or useful depends on the specific context and the properties of the manifolds you wish to study. Indeed, assuming a one-to-one correspondence for identified boundaries is a convenient simplification and can streamline the analysis and understanding of the resulting topological manifolds. However, it does impose limitations by excluding more complex and potentially interesting topologies that arise from non-one-to-one identifications. The resulting manifolds are easier to visualize, describe, and analyze. There is consistency. It ensures that the manifolds are smooth, except for the intended singularities, and that local neighborhoods behave predictably. The calculations of invariants such as the Euler characteristic, homology, and homotopy groups is straightforward. But exploring beyond the one-to-one correspondence, there is a richness of topology allowing more complex identifications that can reveal a richer set of topological structures which might be relevant in certain advanced studies in topology or applications in physics and other fields. the singularities and the branch points which are introduced can provide a deeper understanding of manifolds with these features. These can be essential in areas such as algebraic geometry or in the study of special manifolds. The flexibility of non-one-to-one identifications allows for branch surfaces where multiple sheets come together at branch points, common in the study of Riemann surfaces. When working in topological spaces, especially in the computational setting, it might be practical to initially assume a one-to-one correspondence for the simplicity and clarity. However, for more advanced or specialized applications, it is beneficial to consider and study the effects of more complex identifications. While the one-to-one correspondence is useful and a simplifying assumption, exploring beyond it can open up a wider range of topological phenomena and provide deeper insight into the nature of manifolds and their properties. Balancing simplicity with the potential richness of more complex identifications can be key to advancing understanding in both theoretical and applied topology. When the identification is made, the measures of the boundaries must be considered. For the identification to be smooth and coherent, the metric must allow for the local measures and angles to be preserved in a way that aligns with identification. Multi-valued functions, like the logarithm, can be represented on Riemann surfaces, which inherently have branch points where multiple values converge, identifying the multiple edges to a single edge, which creates a similar structure with the branch points. Identifying multiple boundaries with a single can be thought of as creating a branched covering of the manifold. This is common in complex analysis and algebraic geometry, where manifolds have branch points where the sheets of the surface come together. The resulting topology from such can be more complex and rich, introducing singularities and branch points. The metric must accommodate these identifications, meaning that it must allow for the smooth contraction or expansion of measures and the maintenance of local geometric properties. This type of identification and resulting structure can be useful in various fields, including complex analysis, algebraic geometry, theoretical physics, where non-trivial topologies can play a key role. The idea is to extend the simple one-to-one correspondence into a more complex and rich topological and geometric framework. This can involve considerations similar to those found in branched surfaces, Riemann surfaces, or generalized cones, where the metric and local properties must be compatible with these identifications. This approach opens up a wide range of possibilities for exploring understanding complex topological structures. Identifying boundaries of a region to form a quotient space can indeed lead to the formation of a quotient manifold. But whether or not the result is actually a manifold depends on how the identifications are made. A quotient manifold is obtained by taking a manifold and forming a new space by identifying the points according to some equivalence relation. And for the result to be a manifold, the identification must satisfy certain conditions, such as a local homeomorphism, where the quotient map, which projects points on the original space to their equivalence classes, must be a local homeomorphism property. And the Hausdorff condition, obviously, which with the resulting quotient space must be a Hausdorff space, where any two distinct points must have a disjoint neighborhoods. And the compatibility with the manifold structure, where the quotient topology must be locally look like a Euclidean space. So consider the scenarios where we have the one-to-one correspondence, which is a simple identification when the boundaries are identified in a straightforward manner, and the resulting space is typically a manifold. Now, the other scenario is the non-one-to-one identification, where identifying in multiple ways requires the metric compatibility, which may result in the quotient space not necessarily being a manifold. And there can be more complex branch points in such a way that multiple sheets are converging at a point. For the manifold outcome, the identifications are such that each point in the quotient space has a neighborhood homomorphic to an open subset, so it's a manifold. This typically happens with the simple one-to-one identifications. However, if the identifications create singularities or branch points where the local structure is not Euclidean, such as multiple boundaries converging, the result is generally not a manifold. Instead, it is a more complex topological space with singular points. To determine if the quotient space is a manifold, you can try to construct local charts around each point. If you can cover the entire space with charts that locally resemble the Euclidean space, the space is a manifold. So if you look for points where the local structure deviates from Euclidean space, such as singularities and branch points, these indicate the space is not a manifold at those points. The process of identifying boundaries in the bulk can indeed characterize a quotient manifold, provided the identifications meet the conditions necessary for the quotient space to be a manifold. The simple one-to-one identifications usually lead to manifolds, while more complex identifications involving non-trivial mappings can introduce singularities or branch points, resulting in spaces that are not manifolds. The key is to examine the local structure around each point to determine if the resulting space maintains the properties of a manifold. In the context of fiber bundles, the concept of a quotient manifold and the fundamental domain are closely related, though they play distinct roles. So if the fundamental domain is a specific region of a space from which the entire space can be constructed by applying certain symmetries or identifications, in the context of fiber bundles, it's often used to define the base space and how the bundle's fibers are structured over it. As a fiber bundle is a space that locally looks like a product space but may have more complex global structure. It consists of a base space and a fiber space and a projection map where the total space from the total space of the bundle onto the base, basically, and the local structure around each point of the base space combines into a unified global structure, which can be more complex due to the way the fibers are attached. The quotient manifold can be understood by using a fundamental domain and applying an equivalence relation to its boundary. This process effectively glues the boundaries over the fundamental domain together according to specific rules. The quotient manifold from the fundamental domain defines how the fibers are attached over the base space. The identification of the boundaries in the fundamental domain dictates how the fibers are twisted or glued in the global structure. In the context of fiber bundles, the fundamental domain is used to define and construct the base space of the bundle, and the quotient manifold describes the global structure resulting from identifying boundaries in this domain. The quotient manifold is essentially a result of applying specific identifications or symmetries to the fundamental domain, which determines the overall topology and structure of the manifold. The fundamental domain provides a local perspective, where the quotient manifold describes the global result of these local identifications and symmetries. While specifying identifications on the boundary of a fundamental domain is a useful convenience, especially in the context of describing and constructing quotient manifolds, it is not always necessary. In many cases, particularly when dealing with the fundamental domains in simpler settings, the identification at the boundary provides a clear and practical way to describe the global structure of the quotient manifold. This method allows for intuitive visualization and construction of the resulting quotient space. In more complex scenarios, identifications may occur within the interior or the fundamental domain region or through other means that do not directly involve boundary identifications, and this is particularly true for more intricate or higher dimensional cases. And in the case of complex quotients or higher dimensional manifolds, the identification may be based on a more sophisticated relationships or symmetries that are not limited to the boundaries. And A fundamental domain is a region of space that, under the action of a group of symmetries, can be used to construct the entire space. It provides a local snapshot of how identifications or symmetries affect the global structure. And the fundamental domain helps in understanding and constructing the base space of the fiber bundle and its quotient. Quotient manifolds constructed by taking the space and applying the equivalence relation in a specific way, such which can be varied and does not have to be restricted to boundary identifications. So in the simple cases, the identification of the boundaries is straightforward for certain classical examples, but for more complex spaces, the equivalence relations might involve more intricate patterns, such as identifying points or regions within the interior. While identifying boundaries is practical and common in method for constructing the quotient manifold in simpler cases using a fundamental domain, it is not a universal requirement. In general, identifications for the quotient manifolds can be more complex and need not be restricted to the boundaries of the fundamental domain. The fundamental domain provides a local perspective and basis for understanding how the global structure is formed, but the specific identifications can vary widely depending on the context and the nature of the quotient space being studied. Non-locality in a fractional dimensional manifold, or more generally in spaces with a fractal or fractional dimensional characteristics, can indeed correspond to a form of quotient identification. Fractional dimensional spaces, often called fractals, have dimensions that are not whole numbers. These spaces exhibit complex, self-similar structures at various scales. They are typically not smooth and lack the local Euclidean structure of classical manifolds. Non-local interactions are inherent in these spaces due to their fractal nature. The non-locality refers to the property where points or regions in a space are related or interact in a way that does not depend solely on their immediate vicinity. In fractal spaces, points that appear far apart in a conventional sense might be closely related due to their self-similar and recursive structure of the space. A quotient manifold is formed by taking the space and identifying the points according to an equivalence relation, and this can result in new topological or geometric structures. The identifications can simplify or compactify the space, often revealing symmetries or reducing complexity. Quotient identifications can create non-local relationships by collapsing distinct points or regions into a single point, or by creating complex connectivity patterns. This process can introduce or mimic the non-local properties seen in a fractional dimensional space. The Cantor set is a classical fractal created by iteratively removing the middle third of a line segment. Points within the Cantor set can be closely related through the recursive construction, despite being far apart in the original segment. This non-locality can be seen as a form of identification where points are grouped based on the construction rules, or the Sierpinski triangle, where the fractal is built by recursively removing triangular subsets. Similar to the Cantor set, points within the Sierpinski triangle exhibit non-local relationships, identifying points based on their recursive generation, which can be viewed as a quotient operation reflecting the non-local structure. The fractals in higher dimensions, such as the Menger sponge, involve recursive removal of regions in higher dimensional spaces. The non-local interactions become more complex due to the higher dimensional structure. Non-local relationships in these fractals can be understood through the equivalence relation that reflect the recursive construction. A non-locality in the fractional dimensional manifolds or fractal spaces can indeed correspond to a form of quotient identification, and the recursive, self-similar nature of fractals inherently introduces non-local relationships which can be understood through the equivalence relation akin to those used in the forming of the quotient manifolds. By viewing the construction of fractals as a series of identifications or equivalence relations, one can see how non-local properties emerge naturally in these spaces. This perspective highlights the deep connection between the fractal geometry, non-locality, and quotient topologies. Boundary conditions in the context of differential equations can indeed introduce the non-local phenomena, especially when considering how solutions behave at or near the boundaries. Here's an in-depth look at how boundary conditions relate to non-local phenomena and the breakdown of the usual Euclidean topology at the boundary. Boundary conditions specify the behavior of a solution to a differential equation at the boundaries of the domain. Common types include the Dirichlet boundary values specified, or the Neumann derivatives, or mixed boundary conditions, Robin conditions, and so on. They are essentially for well-posedness of boundary value problems, ensuring unique and stable solutions. Non-locality refers to interactions or dependencies that are not confined to a small neighborhood but involve distant points in the domain. The boundary conditions can introduce non-locality because the behavior of the solution throughout the domain can be influenced by conditions imposed at the distant boundaries. In Euclidean topology, an open set around a point does not include the boundary if it is an interior of the domain. At the boundary, the concept of open sets changes because neighborhoods of boundary points include points outside the original domain. This leads to a different topological behavior at the boundary. The influence of boundary conditions can propagate throughout the domain, affecting the solution in a non-local manner. This means that changes at the boundary can influence the entire solution, not just near the boundary. The usual locality of Euclidean topology breaks down at the boundary because the boundary conditions impose global constraints that the solution must satisfy. The solution is influenced by the values of the entire boundary. This global constraint impacts the solution throughout the domain. Operators like integral operator inherently introduce non-locality because the value of the solution at a point depends on an integral over the domain, which can be influenced by boundary conditions. The solutions to integral equations often depend on boundary values, leading to non-local behavior. Those involve also fractional derivatives of non-integer order, introducing the non-local interactions naturally itself. And in fractional differential equations, the boundary conditions also play a crucial role, of course, for further emphasize the non-local nature of the solution. Boundary conditions on differential equations indeed introduce non-local phenomena, as the behavior of solutions is influenced by constraints imposed at the boundaries. This non-local influence breaks down the usual Euclidean locality, especially at the boundaries where the topological behavior changes. The global impact of boundary conditions means that they must be considered carefully to understand the full solution behavior in the domain. This non-local aspect is crucial in many applications and theoretical considerations of differential equations. This is a valuable perspective for understanding non-local quantum information on the boundary of a hologram, especially in the context of the holographic principle and the ADS-CFT correspondence in theoretical physics. The holographic principle suggests that all the information contained within the volume of a space can be described by data on the boundary of that space. This principle is central to various theories of quantum gravity. It implies a deep connection between the bulk, or the interior of the space, and the boundary, where the boundary encodes all the information about the bulk. This is a specific realization of the holographic principle, proposing a correspondence between a type of quantum field theory defined on the boundary of an anti-de Sitter space and a gravitational theory in the bulk ADS space. In this framework, the boundary theory is highly non-local, encoding the bulk physics, including gravitational interactions. In differential equations, boundary conditions influence the entire solution, demonstrating non-local effects where the behavior at the boundary impacts the bulk. The usual Euclidean topology changes at the boundary, reflecting how boundary constraints affect the global structure. In the holographic principle, information about the bulk is encoded on the boundary. This boundary information can be seen as imposing boundary conditions that affect the entire bulk. Just as boundary conditions in differential equations lead to non-local phenomena, the boundary data in a holographic setup leads to a non-local quantum information that describes the bulk. Boundary conditions on the domain edge dictate the behavior of solutions throughout the domain. Boundary data dictates the behavior of the bulk in an ADS space, showing how non-local quantum information on the boundary governs bulk physics in a conformal field theory. The non-local effects arise because changes at the boundary can influence the entire domain. Non-local quantum effects arise because the entire bulk's information is encoded on the boundary, leading to non-local interactions and correlations in the boundary theory. The breakdown of Euclidean topology at the boundary reflects the non-local constraints, and the boundary in holographic theories acts as a lower dimensional screen that captures higher dimensional bulks information, emphasizing the non-local encoding of information. The concept of non-locality in boundary conditions for differential equations provides a useful analogy for understanding non-local quantum information on the boundary of a hologram. Just as boundary conditions influence the entire solution in a non-local manner, the boundary data in the holographic theories non-locally encodes the bulk information. This perspective helps illuminate how the holographic principle and the ADS-CFD correspondence demonstrate the deep connection between bulk and boundary in these theoretical frameworks. Viewing the quotient topology as having ghost elements or a ghost topology is an insightful way to understand the non-local and often subtle relationships imposed by quotienting. This perspective can help illustrate the nature of open sets in quotient spaces and how they relate to the original topology. In a quotient topology, the open sets of the quotient space are defined such that their pre-images are under the quotient map, which are open in the original space. This involves creating a new topology based on the equivalence relation on the original space. If a topological space has an equivalence relation, the quotient space consists of an equivalence class of that space, and the open sets of the quotient space are those whose pre-images are the natural projection under the natural projection map are open in the original topological space. Now, the idea of a ghost element is a metaphor for how points or sets in the original space influence the topology of the quotient space, even though they may not be directly visible or distinguishable in the quotient space. Open sets in the quotient space can be thought of as having ghost elements because their definition depends on the pre-images on the original space. These pre-images may contain points that are identified or collapse in the quotient, creating a non-local influence. When points are identified, the influence of these points is spread across the equivalence class. This creates a form of non-locality because the properties of the open sets in the quotient space depend on the entire equivalence class and not just individual points. The ghost elements are the remnants or influences of the identified points in the quotient space, akin to the ghosts that affect the topology indirectly. In the original space, open sets are standard open sets in the usual sense, and in the quotient space, an open set means that the pre-image under the quotient map or the projection map is open in the original space. The open set in the quotient space thus carries the ghost influence of the points in the original space that were identified. For more complex quotient spaces, such as orbifolds or other spaces formed by identifying multiple regions or points, the ghost element represents the non-local influences of these identifications on the topology. The non-local effects can include the complex connectivity and the topological features that arise from the identifications, such as the singularities or other non-trivial topological structures. In the holographic principle, the boundary encodes information about the bulk. This can be seen as the boundary carrying ghost information about the bulk's interior, where non-local quantum information is captured on the boundary. Just as open sets in the quotient spaces carry ghost elements, the boundary theory in holographic theory reflects the non-local influence of the bulk. Thinking of the quotient topology as having ghost elements provides a metaphorical way to understand how points or regions in the original space influence topology of the quotient space. This perspective highlights the non-local and often subtle relationships imposed by quotienting, similar to how boundary conditions in differential equations or boundary data and holographic principles influence the entire space. The idea of ghost elements helps capture the essence of these non-local influences in a quotient topology. The quotient topology involves collapsing or identifying points in a space according to an equivalence relation, creating a new topological space where open sets in the quotient space are defined by the openness of their pre-images in the original space. Now, the ghost elements are the remnants or influences of the identified points that affect the topology of the quotient space. They represent non-local interactions and constraints within the quotient space. The boundary conditions of differential equations specify behavior of a domain leading to non-local influences on the entire solution of the differential equation. The ghost boundary conditions influence can be thought of as ghost elements that affect the solution throughout the domain, reflecting how constraints at the boundary propagate non-locally. The holographic principle states that all information within a volume of space can be encoded on its boundary, and the boundary of the holographic theories carries ghost information about the bulk, influencing the entire space non-locally. The ADS-CFT, or anti-de Sitter conformal field theory correspondence, is a specific realization of the holographic principle where a boundary theory or conformal field theory encodes the bulk, the anti-de Sitter space information non-locally. And in the fractional dimensional spaces with non-integer dimensions or fractals that exhibit complex self-similar structures, the ghost non-locality is exhibited by points in fractal spaces that have non-local relationships due to the self-similar and recursive construction, which can be understood through the ghost elements representing those complex interactions. Ghost elements in a quotient topology and boundary conditions represent non-local constraints and influences that propagate throughout the space. In quotient topology, open sets in the quotient space are defined by their pre-images in the original space, containing ghost elements that reflect identified points or regions. The usual Euclidean topology breaks down at the boundaries or under quotienting, where ghost elements introduce non-local properties and interactions. Identifying the boundaries involves ghost elements that represent non-local influence of these identifications. Boundary conditions act as the ghost elements that non-locally influence the entire solution space. The boundary of a holographic space contains ghost elements that encode the bulk's non-local quantum information. Fractal constructions involve ghost elements that reflect their non-local self-similar structure. Ghost topology terminology provides a metaphorical framework to understand non-local influences in various contexts. Quotient topology with ghost elements represents the influence of identified points. Ghost boundary conditions reflect non-local constraints on solutions, and the ghost boundary information encodes the bulk's non-local quantum data for holography. The ghost non-locality of fractals captures the complex self-similar relationships in fractal spaces. This perspective highlights the underlying non-local interactions and influences that arise in the topological and physical settings. And that is my abstract ramblings on ghost topology.